Deep underwater, a dense, heavy metal mass drops out of the pitch darkness and violently collides with a solid granite rock. That impact creates an immediate kinetic shockwave. With the energy blocked by the rock, it shoots directly upward along the attached line. Tungsten is 1.7 times denser than lead, taking less space for equal mass. This causes a perfectly elastic impact. The microscopic contact time creates massive peak force. Tungsten generates a sharp, high-frequency spike. Deforming lead produces a flat, low-amplitude wave. The weight at the end of the line functions as a high-resolution transducer. It translates the physical composition of the ocean floor into raw kinetic data. That raw data now has to climb hundreds of feet through a dark water column before it can be read at the surface. But the moment that wave attempts to leave the solid metal and enter a polymer fishing line, it hits a physical barrier. In acoustics, this is known as an impedance mismatch, a severe clash between a highly dense solid and a much lighter, softer plastic. This diagram shows the boundary between those two materials. Because the impedance gap is so wide, a massive percentage of the kinetic energy literally reflects backward off the boundary, never making it into the line at all. A fraction of the original wave does survive the transfer and begins to climb. Almost immediately, the surrounding hydrodynamic pressure of the ocean bears down on the line, dragging on the traveling vibration. To compound the problem, traditional nylon monofilament is highly elastic. Under load, it easily stretches up to 30% of its original length. As the kinetic pulse tries to travel upward, that stretching polymer physically pulls the wave apart, acting like a mechanical shock absorber and permanently degrading the signal. Zooming in on the molecular lattice of that stretching polymer reveals exactly how the remaining energy is destroyed. As the line elongates under tension, the individual polymer chains slide against each other. This creates internal friction, a process physicists call viscoelastic damping. The kinetic energy of our wave is burned off as microscopic heat. This friction acts as a mechanical low-pass filter. The sharp, high-frequency peaks of the wave, the crisp data we actually want to read, are sheared entirely away, leaving only a muddy, low-frequency hum. By the time that residual hum travels another 50 feet toward the surface, the last remnants of the pulse vanish. The line goes perfectly still. The transmission medium has scrubbed the signal. The high-resolution data generated by the tungsten weight is lost in the water column. Far above the surface, an angler grips a carbon fiber rod, completely unaware of the violent collision that happened below. To feel anything through that rod handle, the vibration must activate a specific set of mechanoreceptors buried deep in the human skin, called Pacinian corpuscles. This frequency spectrum highlights how specialized those biological sensors are. They are strictly tuned to detect vibrations between 60 and 500 Hz. When we overlay the degraded low-frequency wave that survived the nylon line, we can see it falls entirely short of that required threshold. Because the physical wave lacks the necessary frequency, the biological sensors never fire. The human nervous system remains entirely blind to the underwater environment. The engineering challenge is connecting the high-fidelity tungsten transducer directly to the biological receiver without losing the data in transit. The solution relies on a material upgrade. Switching from nylon monofilament to a braided line made of ultra-high molecular weight polyethylene provides a transmission medium with virtually zero stretch. Eliminating elasticity completely removes viscoelastic damping from the equation. The braided line stops acting like a shock absorber and starts acting like a high-fidelity waveguide. The sharp peaks of the kinetic pulse pass right through it, intact. The data generated by the heavy tungsten striking the rock races up the water column and aggressively vibrates the tip of the rod. True tactile sensitivity is achieved by engineering a unified, physically continuous sensory system, carrying the signal from the ocean floor straight into the human nervous system.